Hello and welcome, my name's Rocket and this is the Physics Channel. So, have you ever heard of an atom? Probably, but do you actually know what an atom is? So, today's big question is, what is an atom? Let's make it little. Hi, I'm Rocket and welcome to the second episode of the Big Questions Made Little, and today I'm going to be talking about atoms. So stay focused and don't tamper with the regulator or you'll shrink between the molecules. Let's get started. That was a little reference to a Marvel movie, Ant-Man, which was cool. I got a lot of science wrong, but had stuff to do with atoms, so it was slightly relevant, I guess. Anyway, people all the way back in ancient Greece and we think possibly ancient Egypt, thousands of years ago, have been thinking about atoms. The idea is that if you take any object and you cut it in half, and then you take each half and you cut that into half, so it's now a quarter, and then you take each of those quarters and you cut that in half, you have an eighth, and so on. You keep cutting it in half. How long could you keep going for? Is there a certain size at which you can't cut something in half anymore, no matter what the original object was? People thought you'd eventually reach a size so small that no matter how thin or sharp the blade you used was, you would never be able to cut this thing in 2 or 3 or however more. And so the idea of an atom, something so small you couldn't break it into anything smaller, was born. Of course, now we know that you can split an atom because it's made of even tinier things called protons and neutrons and electrons, and they're made of even smaller things like quarks and so on. But anyway, atoms are still ridiculously small. They're so small you can't actually see them at all. Okay, there are some types of atoms called neutron stars, which are, I suppose, technically isotopes of insanely large atoms, but we're excluding them because they're too big. So, there are 3 main types of particle inside an atom. They're called protons, electrons, and neutrons. Protons have a mass of 1 and a positive charge of +1. The unit for the mass is 1 gram for every 6.022 times 10 to the 23 particles. It's called Avogadro's number. But we tend to just say they have a mass of 1 unit, which is then used for the different masses of all different atoms for all different elements. Neutrons also have the same mass, but as the name would suggest, they are electrically neutral. They have no charge at all. These 2 types of particle exist together in the nucleus of an atom. Now, because these protons are all positive, they want to push each other away. Like how if you have 2 north magnets and you push them together, they'll push themselves away because similar charges repel because electromagnetism. Anyway, all the neutrons want to bring all these particles together. It's kind of like how if you go to Christmas dinner, your granny just wants everyone to be together and enjoy the food and sit around the table and be a family, and your granddad and your uncles and your dad and your cousins all want to just go to the next room and watch the footy or something. It's really annoying. Anyway, so the number of protons in an atom controls what atom it is, what the element it is, which element it belongs to. For example, an atom with 1 proton is a hydrogen atom. With 2 it's helium, 3 is lithium, 4 is beryllium, so on, so on, so on. The number of neutrons inside the nucleus decides which isotope. It doesn't affect the element, but which isotope of that element. For example, an atom with just 1 proton in the middle is hydrogen. If it has a proton and a neutron, it's called hydrogen 2. It's still hydrogen, but it's also known as deuterium. And if it's a proton and 2 other neutrons, then it's called hydrogen 3 because it has a mass of 3 grams for 6.022 times 10 to the 23 atoms, and that's called tritium, I believe. The number of electrons in the atom that are going around is equal to the number of protons in an atom which means the entire overall charge is 0 because you've got all the negative electrons and all the positive protons in the middle. But atoms do gain and lose electrons when they become ions in this case, because there are more protons or less protons than there are electrons. And this happens in chemical reactions or in chemistry and physics. So to clarify, protons control the element and they're positive, neutrons control the isotope and they're neutral, and electrons control whether or not it's an ion and they are negative. So anyway, this nucleus is really, like, it's incredibly tiny. It is really small. Even compared to the atom as a whole, the nucleus is so incredibly small. If all the protons and neutrons in a carbon atom were about 1 meter across, the nucleus would probably be about 3 meters across. The atom as a whole would be 30 kilometers in diameter. If you had a hydrogen atom and the proton was 1 centimeter across, the electron would be going around at a distance that's well, the same as a 100-meter running track with a 1 centimeter nucleus. That's really, like, that nucleus is really small when you consider how tiny atoms are. Now, these electrons that are going around the outside, these things are, they're even smaller. Their mass is so small, it's usually just ignored. Even when we're comparing the tiny masses that protons and neutrons have, we just say it's that the electrons have no mass. They do. It's about 1/2000th of the mass of a proton or neutron. But we usually just ignore it completely. They have a negative charge of -1, which is equal but opposite to the charge of a proton. And they just sort of orbit the nucleus in shells of energy, with electrons with more energy further away and electrons with slightly less energy a bit closer to the nucleus. They're all held in place by this electromagnetic force, holding them as they go round and round and round, and they move at about 0.3 miles an hour, which is how fast a snail moves. But if you consider how small these atoms are, how these tiny distances they're travelling, actually, compared to how many orbits they do, they're going really fast, because they're crossing these tiny distances in really small amounts of time. Just going round, even though they're actually going pretty slow. Anyway, electron shells have patterns. You can only possibly have 1 or 2 electrons on the innermost shell. You can have 1, 2, 3, 4, 5, 6, 7, 8 on the second shell, 1 to 18 on the third, up to 32 on the fourth, 50 is the maximum on the fifth, and 72 is the maximum number of electrons you can have on the sixth shell. But atoms don't always follow this rule, don't always follow this pattern. For example, in a gold atom, the number of electrons in each shell is 2, 8, 18, 32, which follows, and then 18, 1. It's really weird. It has loads to do with the properties of the atoms, the fact that the further away atoms the electrons are, they have more energy, and the further away it's harder for the neutrons to hold the nucleus to hold on with the electromagnetic forces. It's a really complicated physics. It's got a lot of factors in it. It's difficult to explain in a YouTube video. And as Yoda said,
try not. Do or do not. There is no try.
So I will not try. I will not. I will not try. I just will not. Anyway, electrons are extra confusing because they're not actually particles. Sometimes they're particles, but sometimes they're waves. They're just bits of energy. In this very clever thing called the double slit experiment, scientists fired loads of these tiny electrons at a single slit in a piece of metal and a surface with a sensor behind it, and this sensor detected a line of electrons where they'd emerged on the other side. Then they fired all these electrons again through these pair of slits in this surface with a sensor behind, and they got this wave pattern appearing as they'd sort of distorted one another and interacted and interfered with each other as they passed through these slits, like water particles in the wave on the ocean reacting with each other. Now, these scientists, clever clocks, decided to find out what would happen if they fired these electrons one at a time through the double slits, thinking they'd have these 2 rows behind them on the sensor. But when they fired each electron one at a time, there were wave fronts forming again. The individual electrons were somehow becoming waves, reacting with themselves as they passed through the slits, and then hitting the back wall again as particles. Basically, each electron went through the left slit, the right slit, both slits, and neither slits, all simultaneously. The scientists observed what was going on, seeing what each electron did at the slits, and then all physics broke. When they looked at the electrons going through the slits, they went through one or the other, and they formed 2 rows on the sensors. They remained particles. And yet, when the scientists didn't observe, the electrons became waves and did all the weird stuff. And we have no idea whatsoever why this happens. The best explanation is that the act of observing changes an experiment. But that's not an explanation. That's literally just stating the obvious of what's going on. And to be honest, it's just really confusing. Electrons are pretty weird things. But that's it for Atoms this week. Next week will be the last episode of me for this year. But Rock and I will be back in January with some new episodes. And I'm going to be starting a 2-year series next year, where I'll be talking all about the elementary particles. And I'll be introducing those and talking about what elementary particles are next week for my last episode of 2016. So, I'll see you all next week though, guys. Bye.